Recording in progress.
All right. So today's a review of chapter 5. It's about free body diagrams and equations of motion. Am I coming across okay in the back? Can you hear? Okay. So the most important thing is to do a good free body diagram. And the technique to do that is to, here's the problem statement. It shows you, in this case, a couple of links. Both of them are penned. And you draw an imaginary line around the entire object. And wherever you cross a force or a support, in this case, this pen and this pen right here, you need to replace that support with its support reactions, which are given by these tables. Remember, we went over these already in class. I'll give you these tables on the test. This one for 2D and also this one for 3D. So you don't have to worry about that. And then the next step is, of course, coordinate system. But when you're drawing your free body diagram, when you cross this pen C, you might think, oh, I got to put two unknowns there because it's a pen, but I already got two, so I must have made a mistake. Let's did this earlier. So in this case, you were drawing you came across this support A, so you put in the two support reactions. Doesn't matter which direction you put them. I always put them positive, but it doesn't really matter. And then you keep going around. This is joined together. I'm drawing a free body diagram of the entire thing, so I ignore that joint at B. And then I go to C and say, oh, it's another pen. I need two unknowns there, but then you should click right away. That means I have four unknowns. And this is a 2D problem I can only solve for 3. So you say, oh, there's something weird about two force members, right? So if you take this length BC and draw a free body diagram of it, the reactions at each end have to be equal and opposite. Otherwise, that link is going to move. So therefore, you know that the force in this link is at 30 degrees. So instead of putting, I see what he did. He broke up this thing into two objects. So now we're just drawing, we're drawing just a free body diagram of A, B, and we realize that link BC is a two force member. So we replace that link in this case with a 30-degree. But notice that I could have drawn the free body diagram of the entire thing, and I could have put that force here. But that's a sliding vector. So these two are exactly equivalent, right? So it didn't matter in this case if you drew a free body diagram of A through C or A through B. And you replace, you put all the known forces on there, and you also put the dimensions on and the coordinate system. Once that's done, and that's not an easy task in some cases, then the next step is to do your 3 equations of motion. Summon forces in X and Y, and summon moments about any point and setting it equal to 0. The trick is when you have a problem like this, is when you're summing forces and summing moments, you should choose let's say moments. That's the most important. When you're summing moments, try to choose a point about which most of the unknowns go away, which means they pass through that point. In this case, you should sum moments about A, because the only unknown then is going to be By. In this example, P2 and P1 are known. And likewise, summing forces in the X direction, there's only one unknown in the X direction. So automatically you figure out, well, AX is equal to P2, and I can solve for By rather, by summing moments about A, and then I can sum forces in the Y direction. Dot. 3D is the same, except you just got to extend it into another dimension. The 3D support reactions are shown in this table, and be particularly sensitive to the journal bearings versus thrust bearings. The difference is the thrust bearing can support a load along its rotational axis, whereas a journal bearing cannot. Right? A journal bearing cannot support a force along this axis. All right. And then we talked a little bit about static indeterminacy. For instance, when a beam, in this case, is over constrained, it's over supported, right? I've got three unknowns at this diving board interface, right? I've got the unknown reaction moment, and I've got two forces in X and Y, plus I have two rollers. That's five unknowns. So this thing is not, you can't solve for this in this class. When you start taking MEs, like I said, taking solid mechanics, there are techniques to do that, but beyond the scope of this class. All right, so let's just do some examples. So the roller at B can sustain a maximum load of 3 kilonewtons. So you say, all right, the reaction at B is 3 kilonewtons. That's the maximum allowed. What is the largest magnitude of the three forces? So this one's a little backwards. He's telling you one of the reaction forces and asking for one of the applied loads, or in this case, 3 applied loads, but notice they're all the same magnitude. So the next step is to draw a free body diagram. And especially if you use different colored pens on your test, you can just draw it right on here. Right, so that's the reaction at B, and I know it's at 45 degrees. There's a reaction at A, so it's A X, A Y. I've already established my coordinate system, X, Y, and that's it. That's a good free body diagram. I've got the three forces. I'll just put them in red so they're highlighted. So I've got a coordinate system. I've counted my unknowns, and I'm in 2D. It's less than 3. That's the next step, right? After the free body diagram is done, is count unknowns. In 2D, it's 3 max. And in 3D, it's 6 max. So in this case, I have 3, right? AX, AY, and F. Because what I'm going to do is, he tells me B is going to be, if the maximum value is 3 kilonewtons, and he wants to know what is the largest magnitude of these applied forces F. That means that I can set B equal to 3 kilonewtons, and that'll solve for the maximum forces F. So I'm going to do that. So I'm going to say, all right, B is 3 kilonewtons. And now your next step is to, I always look at the moment equation first because it's going to be the most powerful, because it's going to allow you to get rid of possibly 2 unknowns, whereas in the X direction and Y direction, it doesn't really work out that way. In this case, it does, since you know B, so you could solve for AX. And, you know, right? But we don't need AX. We don't need AX. He didn't ask for them, right? Regardless of your thought process, you should immediately go to point A and say, I'm going to sum moments about A because I know B and I know that the moments due to those 3 forces, I can solve directly for F. There's only one equation needed in this problem. So summation moments about A is 0. So again, you need to break up this guy into his 2 components, right? This is 3 cosine 45, and this is 3 sine 45. Well, the vertical one, the 3 sine 45, passes through A, so it has no moment. The only one that has a moment is the vertical component, which is 3 cosine 45, and it's 2 meters away, so that is 3 cosine 45 times 2 meters, and then you realize it's this guy. He wants to go clockwise around A, so it's a negative moment. And then you've got the moments due to the 3 forces F. You realize all the F forces want to go counterclockwise around A, so they're all going to be positive. And they're varying distances away from A, but that's pretty straightforward. So now we'll just say plus 2 times F, plus 4 times F, plus 6 times F, right? 2 plus 2 plus 2 is 6. 2 plus 2 is 4. And now you can solve this for F. 0.354 kilonewtons. So I hope you see how your thought process is important when you're approaching these problems, especially when you're drawing your free body diagram, counting your unknowns, making sure that they're valid, and then choosing what point you sum moments about wisely. Any questions? All right, what are the reactions at the supports A and B? Okay, so I got a distributed load here, so I need to figure out how to break that up. Let's just do that first. So let's do it in green. I'm going to take one shape as this one, this big, long rectangle. That leaves me with a triangle instead of a trapezoid, so it's easier. So that height is 200 Newton meters. It's 4 plus 3 meters long. So 7 times 200 is 1,400. So it is, this is 1,400. This is the resultant of the triangle. And it's halfway in the beam. So it's 3.5 meters from here. And now we're going to switch to blue and we'll do the triangle. Well, the triangle resultant force is 1/2 the base, which is 3, times the height, which is this amount right here, which is 200 newtons per meter, right? Some people make a mistake and make that 400, but remember, we took care of this area down here earlier. So it's 1/2 the base times the height, so this is 300, right? Yeah, 300 newton. And the centroid of a triangle is 1/3 from the fat end. So I'm 3 meters long, so that means that this distance is 1 meter, and this distance is 2 meters. Next step is my coordinate system, X, Y. Draw the free body diagram. Let's just do it in orange. So there's a pen here. So AY, AX. And there's a roller at B. So its only reaction is a normal force. I just call that BY. Next step, count your unknowns, AY, AX, BY, 3 unknowns, we're good to go. Next step, choose a point where when you sum the moments, most of the unknowns go away. In this case, it's summing moments about point A, just like in the previous one. So that's what we'll do first. Summation of moments about A is equal to 0. Let's take the 1,400 Newton one first. It's 3.5 meters away and it wants to go clockwise, right? So it's a negative moment. So this is minus 1,400 times 3.5. Likewise, the 300 Newton resultant force for that triangle wants to go clockwise. So it's also a negative moment. So minus 300 times its distance from A, which is 3.5 plus 2 or 5.5. And then there's the reaction at B, which is 7 meters away. It wants to go counterclockwise, so it's positive, so plus 7. Solve for BY. So solve for BY, 957.1 newtons. Now I can just sum forces in the X direction, set that equal to 0. There's only one, the Penn reaction at A. So A sub X is 0, and then sum forces in Y. Set that equal to 0. So I have minus 1,400, minus 300, plus BY, which is 957.1 plus A1. So AY is 743. Yeah.
So I think for the moment, like for the triangle, it could be at 6 meters since when it goes couple of
yeah.
like from
Yeah.
like 4 meters, then like
Yeah.
2 over 3
You're totally right. I made a mistake. Thank you. This is 6. Good catch. I said 3.5 plus 2, but it's really the 4 plus the 2, right? I drew this wrong. This should be 2 meters right there. So good reason to go back and check your problems after you do them. I mean, I had it written down correctly and I even did it. So go figure. So thanks for that. Good. All right. Determine the normal reaction at roller A and the horizontal and vertical components at B for this member. Guess we're doing okay on time. This one's very, the next two are really similar. But I think we have enough time, so we'll just go for it. So I'm gonna draw a free body diagram first. So he told me there's a pin at B, so BY, BX. The loads here, let's highlight those in red. And the roller at A, so it has a reaction only in the Y direction. There's my coordinate system. Count the unknowns. I have 3. So we're good to go. First step, some moments about some magic point. And in this case, we want some moments about B because that gets rid of 2 unknowns, BX and BY. So let's do that. Some moments about B. That's equal to 0. So the 6 kilonewton force, you might be tempted to break it into its X and Y components, but no, you already have the perpendicular distance, 0.4 meters, right? 0.4. And that wants to go clockwise around B. So that's a positive moment. So it's 6 times 0.4. The 10 kilonewton force, we need the, we need this distance and this distance here. The entire length of the bar is 1.2. So this distance is 1.2 cosine 60. And this distance here is 1.2 sine 60. So the 10 kilonewton force, its perpendicular distance is the 1.2 cosine 60, this guy right here, right? So 10 times 1.2 cosine 60 plus the additional amount, 0.6, right? Plus 0.6. And that is also a positive moment, right? It wants to go counterclockwise around B. Now we have AY. It wants to go counterclockwise, keep getting that backwards. So it's a negative moment, so minus A. And its perpendicular distance is 1.2 cosine of 60 plus these two, 1.2, right? So it's minus 1.2 cosine 60 plus 1.2. We can solve this for A. That's AY. No, that's just A. Yeah, AY. Okay, yeah. AY is 8 kilonewtons. And then we sum forces in the X direction, set that equal to 0. So I've got the component of the 6 kilonewton load. It's at 30 degrees from X-axis because it's perpendicular to this length, which is 60 degrees from the X-axis, right? So its X component is 6 minus 6 times cosine 30 plus BX. So BX comes out to be 5.20 kilonewtons. And then lastly, some forces in the Y. So I have AY, which is 8 kilonewtons, minus 10, minus 6 sine of 30, plus BY. So BY comes out to be 5 kilonewtons. Made a mistake. Correct it next year, minus 10. Yeah, pretty straightforward. Yeah.
For the moments about the equation, you have 6 times 0.4, that looks like equals to.
Oh, yeah, it's
Is that
plus. Thank you. Good. This one's really almost the same. We'll just do it. So free body diagram, I have a roller at B, so there's a normal reaction. And I'm just going to draw it up even though it's down, but it's fine, right? There's a reaction at A, we have a pen, so there's AY and AX. Coordinate system, X, Y. Count unknowns, I have 3 unknowns. So I'm good to go. Now, choose one of the equilibrium equations that will get rid of the most unknowns. In this case, it's summation of moments about A, right? Because now I can solve directly for BY without any simultaneous equations. So BY, actually, I drew it down on my paper here, so I'm just going to change this to down. Okay. Doesn't matter. It would just come out negative. So I can work in inch pounds. I don't have to convert to feet. You can work in inch pounds here. So the moment due to BY is 18 inches away from the point A, and it's clockwise, so it's negative. So it's minus 18 BY. So now they have this funky force here, 50 pounds at 30 degrees. So I'm going to just on the fly here. I'm going to break it up into its components. So this is 50 cosine 30, sine 30, sorry. The reason I know that is it's going to be the smaller of the two because the 50 pounds is only 30 degrees from the negative Y. So it's going to be bigger. So I know I use cosine here. So this is 50 cosine 30. And now we're ready to choose a point about which to sum moments. And just like before, we should do it about point A because then I can solve directly for BY. I already said that much, right? So here we are, 18 BY. So now I've got 50 sine of 30. It's 14 inches away, wants to go clockwise, so it's positive. So plus 50 sine of 30 times 14. And then the vertical component, the 50 cosine 30, also wants to go counterclockwise. It's also positive, so 50 cosine 30. And that one's 20 inches away. So solve for BY, 67.8. And that's in pounds. And now simple matter, summing forces in X and Y to solve for the Penn reaction at A. So I've got minus 50 sine of 30 here. So minus 50 sine of 30 plus AX. So AX is equal to 25 pounds. And summation of forces in the Y is equal, this is equal to 0. So it's minus 50 cosine 30, right, that guy? Minus BY, minus 67.8 plus AY. So AY is 111. On your test, please circle your answers. Good. 3D. So 3D ones, they're more difficult, they have more unknowns. And there's that funny business where you need to figure out the sign, the SIGN of the moments in the 3D problem. There's two ways to do that. We'll talk about that. So XY components at the fixed wall A. A little confusing, XY components of the reaction to the fixed wall. Well, there's 6 unknowns, right? Because we're at a fixed wall, so there'll be 3 forces, Fx, Fy, Fc, and 3 moments, My, Mz, right? So the free body diagram is going to be tricky here. Let's just try it. So Z, remember you're looking down on Z and you want to rotate counterclockwise. So the moment, this is a reaction. This was confusing last time for some people. There's a moment in the Z direction that pin A, that fixed support A, cannot rotate about the Z axis. Therefore, there has to be reaction moment. And likewise for X, so it'll be MAX. And then likewise for Y, so it'll be MA. Then, of course, there are the 3 force reactions, AX, AY. And that's a good free body diagram. I got a coordinate system already. Count my unknowns. I have 6 in 3D, so I'm good to go. Well, a lot of these are trivial. There's only one force in the Y direction, right? The 200 Newton, and then there's the reaction force AY. So let's just start there. Some forces in the Y is equal to 0, is equal to AY plus 200. So therefore, AY is minus 200 newtons. Likewise, for Z direction, there's only one unknown, the reaction at A. So summation of forces from the Z is equal to 0. So the reaction at A is AZ, and then I have minus 150. So therefore, AZ is 150 newtons. I realized that the 200 Newton force is parallel to Y, so it has no moment about Y axis, and the 150 Newton load in the Z direction passes through the Y axis, so therefore the summation of moments in the Y is 0, and there's only one reaction there, so that's the moment about Y. So the reaction at Y, the moment reaction at Y, the moment reaction in the Y direction at point A is 0. Okay. So I have 2 unknowns left, the moment about the x-axis and the moment about the z-axis, the reaction moments. So I need some moments then about x-axis, set that equal to 0. So the x-axis, so that's this one here. This vector right here is 2 meters underneath the xy plane, and it's pointing in the y direction. So it has a moment about the x-axis of 2 times 200. But you need to know what direction it is. So that means you have to put your eye over here and look back. Along the x-axis. So I'm looking towards the origin, and that guy is underneath me. He wants to go counterclockwise, right? He wants to go this way, which is positive. So it's 200, positive 200 times 2. The 150 Newton force is 2 meters away from the x-axis. The perpendicular distance is 2, but it wants to go, see, I'm looking back at the origin. He wants to go clockwise. So he's negative. So it's minus 150 times 2. Plus the reaction moment at A. So the reaction moment at A is 100 Newton meters. Don't forget to put the little dot between the units. And lastly, some moments about Z, set that equal to 0. So I have the unknown reaction at A. So that's the moment reaction in the Z direction at A. With 150 Newton load is parallel to the Z axis, so no moment. The 200 Newton load is 2.5 meters away from the Y axis, so it gives a moment about the Z axis. If you look down here, it's going to be a positive moment, so plus 200 times 2. So the moment at Z is minus 500 Newton meters. Another way to do this is to use the cross product. If you don't want to worry about moving your eye around on the x-axis and turning around and all that, I can say, well, let's call this force F1. If I want the moment about A, I can say, well, it's the cross product of the vector from here to here, right? Just call that R1. And we know that. So the moment due to force 1 is equal to, and then you can build your determinant. Put in the R vector next, which is going to be 2.5 in the X, 2 and minus 2. I'm doing this on the fly. I hope it's right. Right, I got to go from A to this point in the Y direction. So that's 3, actually. 2.5 and then down 2. And then I put the force. In this case, that force is parallel to the Y axis. So it's 0, 200, 0. And then you could do the same thing for the force 2, right? And that would get rid of kind of this stuff down here. Well, we'll get rid of these sorts of terms, right? You still have to do the summation of moments in X, Y, and Z, but you would have the moments in X, Y, and Z for forces F1 and F2 already by this technique. Am I making sense? So you do I, J, K. In this case, the R vector way is just 2 in the J, so 0, 2, 0, and that force vector is 0, 0, minus 150. So you could do these two first, and then do these 3 moments equations. And then these numbers will already be calculated, these two, from these 2 determinants. Hope that makes sense. I want to give you 2 options. Yeah.
Isn't the moment that's supposed to be negative?
Um, 400, yeah. All right.
Why is it negative if it goes like
I drew it positive, but it just came out negative. So it's actually the other way.
like if you look at the drawing, wouldn't it make sense if it goes counterclockwise?
It's hard to intuit. I've got a positive moment here, and I've got a negative component here. It's not intuitive to me. I think you should let the math work it out. 400 minus 300 is 100. So moment about the x-axis is, yeah. I mean, here's this, 150 times 2 is less than 200 times 3. So that's where that negative moment comes in. All right, good questions. All right, here's on. We're doing well. All right. There are these pesky bearings. So we have a vertical force of 800 pounds, 80 pounds. This guy, he's operating on this crankshaft. He's giving me all the dimensions. What is the equilibrium force P down here that must be applied to the handle and the reactions at the journal bearing A, this one A, and a thrust bearing at B? These words are very important. Journal and thrust because those two have different support reactions, right? So I see that these are bearing problems, and I'm guessing it's well supported, and that which means I can ignore the moment reactions at the bearings. If this bearing A were gone, you would certainly, if you're holding the bearing at B, it's certainly it's gonna want to turn. But once you put in this journal bearing at A, your buddy went over there and he helped you lift that end of that pipe, that crankshaft. So the moments are all going away. And also you know that because you looked at your table, you went and you saw where is it? Oh, 3D. Journal bearing, remember, I'm getting rid of the moment, so it has two unknowns. And the thrust bearing, this guy, remember, I'm getting rid of these moments here. It has three unknowns. The purpose of a thrust bearing is to be able to take a load along the axis about which it rotates. So it's specially designed for that. So that means I've convinced myself I can get rid of the moment reactions, but I need to put in the force reactions.
Yes.
Dang. Oh, it's like it gives up after a while. All right. So I'm going to put a J by this and a T by that. So I remember that it's a thrust bearing. So a thrust bearing at B has three components, By, Bz, and Bx. Journal bearings, they can't move up or down, so they have a reaction. And the C, they can't move along the y-axis either, along the x-axis either, so there's a reaction on the x direction. And then I have the unknown P. So I got a coordinate system, I got a free body diagram, I count my unknowns. The three unknowns at B, there's two unknowns at A, and there's one unknown at P, at the hand. So I have six unknowns. But I'm in 3D, so I'm good to go. Yeah.
So at this moment, it's the moment like we just drop the moment away.
Yeah. Do you get why though?
I guess if it's more than 6, we assume that's like full support system.
Well, just imagine you're the guy holding that thrust bearing, and that there's somebody pushing down here. You're gonna have to. I gotta be the one that reacts to that and keeps that journal bearing still. But once your buddy over here comes over to this point, to the origin, let me help you with that. Lifts up on it. Moment goes away. And it's typically true. I mean, you can't solve for more than 6 unknowns. So most of the time, but not all the time, you get rid of the moment reactions for the bearings. All right, so we're ready to move. We got coordinate system, we got free body diagrams, we've counted our unknowns. Now we're going to choose an axis about which there are the fewest unknowns. We're going to look at the y direction first because there's only one unknown, By. So some forces in the y. So By is 0. All right, easy enough. Let's just move on and just some forces in the x direction. Set that equal to 0. So I've got AX and I've got BX, and I drew them both positive, so AX plus BX. And then I've got P down here, which is in the minus X direction. So that's one equation. Some forces in the Z, set that equal to 0. So I've got AZ and BZ. Oh, and the 80 pound. Now I've got an 80 pound load there, right? So it's A, C. I drew both of those positive, so they're positive, then minus 80. Right? This 80 pound force is in the minus K direction. And now some moments about X. All right. So the reaction at A goes away because both of those pass through A. BY passes through A. So it has no moment. BX is parallel to X, so it has no moment. So the only ones are this one and this one. They give moments about the X-axis. So let's do P first. No, P is parallel. It's BZ, sorry. What happened to my drawing? Yeah, with some of the moments about this axis here. So BZ does have a moment about that axis. You put your eye right here and look back, and BZ's over here. Want to go counterclockwise. And it is 14 plus 14 or 28 inches away. So it's BZ times 28. And then there's the moment due to the 80-pound force, right? It has a moment, the moment arm is 14 inches. Now, if I'm looking back at the origin along the x-axis, he wants to go clockwise. So he's negative. So it's minus 80 times 14. So in this case, I can solve directly for BZ. So therefore, BZ is 40 pounds. And next, I some moments about y-axis, set that equal to 0. Some moments about y. Where's my y-axis? Oh. Okay, so some moments about this axis right here. AX passes through that axis, so does AZ, right? This axis extends all the way here. So there are no moments due to these support reactions at A and B. The only moment about the x-axis is due to this 80-pound load and this applied load P down here, which is one of the things we're looking for. So in some moments about Y, remember my eye is here, I'm looking back towards the axis, so it wants to go clockwise, so it's a negative moment. So minus 80. That's the hardest part, I think, is figuring out the signs of these moments. And then P, about the y-axis, it wants to go, do I have that backwards? Yeah, this one's positive and this one's negative, so minus 8P. So therefore, P is 100 pounds. Right, y-axis, 80 pounds over here. 8P. See, it's really confusing. All right, summation moments about Z is next. If I were confused at that point, I would just build a determinant and figure it out from there, right? And that's easy to do. You're taking the moment about the y-axis, so the R vector would be just 10 minus 10I, 0, 0, and then the force would be 0, 0 minus P. So you could do the determinant thing and figure out those signs here. But anyway, let's move on. So about the z-axis, well, I've got this P down here. And you notice, see, he's 6 inches away plus 4 away from the y-axis. And it wants to go 6 times. It wants to go clockwise, so it's minus 10 times P. And P I figured out was 100, right? This is P. Minus, and then about the z-axis, by passes through the z-axis, bz is parallel, so it's only bx that has a moment, and it's 14 plus 14 or 28, and it wants to go clockwise, counterclockwise rather, so it's minus 28 bx. Therefore, bx is minus 35.7 pounds. And then we go back to equation 1 and solve for ax. So we have 0 is equal to ax plus bx, which is minus 35.7. Minus p, which is 100. Right, so this is p and this is bx. This is equation 1 I'm solving for. Ax is 135.7. The only thing I'm concerned about is getting the correct signs, because even I'm having trouble doing that. Anything else? We got 10 minutes. Oh, no, we have another one. Oh, we have 2 more. Jeez. Let's take a look and see which one. F8 looks like that. That's too much work. Let's just set these up, okay? So let's go do this one first. Now, in this case, the distributed load is a volume. You're used to having them as an area. But now we're in 3D. It's exactly the same thing. The resultant force, let's do it in orange. The resultant force due to the distributed load is going to be acting in the center, because that blue swimming pool is symmetric. So it's going to be equal. But this is the force due to the distributed load. And notice that this is the weighting functions in pounds per square feet, whereas in 2D it's pounds per foot. That's because in 3D you're going to be multiplying by an area. Same principle though. So the area of the swimming pool is 2 by 4, right? So it's 2 times 4 times the weighting function, which is 2. So that's 16 pounds. And we know where it is, right? It's in the center, so this is 2 feet. And this distance here is 1 foot. He tells us I have ball supports at B and C. So let's keep it in red. So there's a ball joint here and a ball joint here. Ball and socket at A. This is a ball and socket. No problem. The rollers, the ball supports at C and D, they just prevent movement in the Z direction. The rollers, you can slide this one pull on the X and Y if the ball and socket joint weren't there. So there's only one reaction at C. I mean, this is a ball joint. So there's a reaction CY and a reaction BZ. Reaction here, BZ. And then the ball and socket at A has, if you go back and look, it can rotate in any axis. The only thing it can do is support forces in X, Y, and Z, because it can't move in X, Y, and Z. So there's A, Y, A, X, and A, Z. Count your unknowns: A, Z, A, X, A, Y, B, Z, C, Z, 5 unknowns. Got a coordinate system. We're ready to go. I summed moments about the x-axis first. Sometimes the moment reaction around X axis, the moment reaction around the Y axis up here, they're both going to involve the unknowns B and C. So, but it's the best you can do because at least the moment due to the ball and socket, lies on the XY axis. So at least those go away. So the first thing is some moments about the X is equal to 0. So remember, I'm here, I'm looking back along the X axis, and I see that CZ down there. It wants to go clockwise. So does B. They both want to go this way, so they're both positive moments. So BZ is, sorry, CZ is 2 feet, is 1 foot away. So this will be CZ times 1. BZ is 2 feet away, so it'll be plus BZ times 2. And then I have the distributed load, 16 pounds. It's 1 foot away from the x-axis. It wants to go clockwise. So it's a negative moment. So it's minus 16 times 1. So that's the best you can do. That's one equation. And then some moments about y. Set that equal to 0. So now I'm some moments about this axis. Remember, I'm here now, looking backwards. So now I've got those moments at B and C going clockwise, so they're both negative. BZ is 2 feet, half of 4, away from the y-axis, so it's minus 2 times BZ. CZ is 4 feet away from the x-axis, y-axis, so it is plus 4 times CZ. That's negative, sorry. Remember I said they're both negative. So I got CZ, BZ. Now I have the distributed load there. So it's over here going down around counterclockwise. So it's positive. It's 2 feet away. So it's plus 2 times 16. So that's my second equation. And then some moments about, doesn't make sense to some moments about the z-axis because all the forces are parallel to z. There's no moments, right? But I realize there's only one force in the x direction and one force in the y, ax and ay. So I can sum forces in the x. Set that equal to 0. So that means that ax is equal to 0. Some forces in the y, set that equal to 0. So that means ay is equal to 0. So you might want to make a table over here in these 3D problems so you can write down all of your unknowns so you can write them down as you solve them. So I got 0, 0. So I got 2 equations, but I still have 3 left. The only thing left to do really is sum forces in the z direction. Set that equal to 0. So I have the reaction at A, which I drew positive, plus CZ plus BZ minus the distributed load 16. So there's my third equation. So I have to solve these 3 simultaneously. And when you do that, you get AZ is 5.33 pounds. BZ is 5.33. Just so happens they're all the same magnitude. Go figure. I did check that and it is right. Any questions? Concerns? We'll just set this one up because it's everything's in your wheelhouse, but you've got to create unit vectors. So I'm just going to kind of set this up. I've got the cable from B to C, and I've got a cable from B to D. So that means the first thing you're going to need to do is get unit vectors between those two. And if you forgot how to do that, you may want to go back to chapter 2, right? This is the unit vector in the BD direction is that way, and unit vector here, unit vector BC. And then I can say, well, FBD, right? That's an unknown, FBD. The force FBD is just equal to its magnitude times the unit vector. And same thing for the force between B and C. It's equal to its magnitude, BC, times the unit vector, BC. So you have to do that first. That takes me half a page to do. Why don't I just tell you what they are? So so in case you want to go off and do this, F1 is 0. Oops. Wanted, did I do it at all? I'll just tell you what the unit vectors are. So U, B, C comes out to be 0, minus 0.6, 0.8. And U, B, D, these are vectors, is equal to 0, 0.6, 0.8. You might recognize that. That's the 3, 4, 5 triangle. And that triangle is anyway, we got running out of time. But now you have to do your summation of forces, summation of moments. And it's very tedious. Okay. Good luck in the test Friday.